Hi everyone, my name is Xinyi Hu, and the topic our group will introduce is the constraint optimization. We will mainly introduce the constraint least squares optimization in this video, and we will use the exercise question in VMLS as an example. The question is shown in the screen. The first solution we will use is the KKT function. In VMLS, we can get the KKT function via Lagrange multipliers, and it looks like this. To build the KKT function in Julia, first we need to determine the size of matrix A and C. Then we use the matrix G to represent the gram matrix of A. According to the KKT functions, we can write the KKT matrix like this. Hence, the matrix containing x hat and z hat can be written in Julia like this function. And the row 1 to n in this matrix is exactly the x hat we need. Solution 2 is to build a QR factorization function by using the KKT function. The function can be rewritten as this. And in Julia, we need to determine the matrix A and C, and then combine the two matrices to make a new one. Use QR to represent the QR factorization matrix. As we know, the row 1 to m is the Q matrix of A in the QR factorization, which we denoted as Q1, and the rest of Q, we denoted as Q2, is a matrix of Q in QR factorization of C. Matrix 2 has a QR factorization too, so we denote Q2 and R2 to represent the QR matrix of Q2. According to the function, we get the omega looks like this, and finally we can get the x hat we needed. Implement the information we need in the question above, and running these functions, we can get the x hat in each method. And when we try to compare these two results, we can find that the norm is 0, which means they are almost the same.
Linear quadratic control, and our objective is to minimize the J. J equals to J output plus rho multiple J input. And at first, we wrote a function named LQR, which constructs and solves the constrained linear squared problems. The function returns three arrays x, u, y. We should notice that yt equals to c multiple xt. We allow the input arguments x init and x destination to be matrices, so we can solve the same problem for different pairs of initial and end states with one function calls. In the number of columns in x initial and x destination is q. Then the entries of the three output sequences x, u, y are matrices with q columns. The ith columns are the solution for the initial and end states specified in the ith columns of x initial and x destination. Then we plot the open loop response. And then we can use Julia to solve the linear quadratic control problem with t equals to 100 and 0 equals to 0.2. And we can get the minimized J input value and J output value.